Did I gain weight?
What was the starting weight?
I'm like 128.
Oh crap.
Oh my god. So fat. Oh wow. It went up to like 140.
142.
Yeah.
It just goes back to normal.
Yeah.
And it went down to like 120.
That doesn't matter.
Yeah, because that's when it's
Yeah.
like slowing down. Whoa. That was like 118?
Yeah, 118.
Yeah. My legs are still shaky from the car.
God damn it.
I'm like falling backwards. Here we go. That was 140.
140.
Yeah.
I don't know why I feel like I'm falling backwards.
Does it feel weird on it?
No, it's like, I don't know, I felt like I was falling backwards when we were going down. Hi, how are you? Alright, here we go.
117.
Yeah.
Okay.
Maybe why was I moving backwards?
Okay. In order to find the acceleration for an elevator going up and going down, we first had to find Cameron's weight. Cameron was our test trial for trial 1 and 2. His starting weight was 128 pounds. We had to convert every single weight we found into kilograms. For trial 1, we found that going up an elevator, his weight increased to 142 pounds, and going down an elevator, his weight decreased to 118 pounds. For trial 2, his weight went up to 140 pounds and his weight went down to 117 pounds. In order to convert pounds to kilograms, I followed this calculation right here. Okay, so with our weight, we converted it to grams, and then from here we converted it to kilograms. We moved on to our trial 1. From here, we broke down the elevator into a stationary position and a position where it went going up. For a stationary position, because our normal force is equal to mass times gravity, we can use this to solve for our Fnet. Our Fnet would be Fn equals m1g. And for our going up position, we did the same thing for Fnet equals ma, but because the normal force is greater than our mass times gravity, we have to subtract the mass and gravity from our original Fn. From here, we used this normal force in our stationary diagram, and we plugged it into our diagram when the elevator was going up. From here, we moved on and eventually got this equation, m1g minus m2g equals m2a. We plugged in our data using the masses we had from up there, and we found, okay, so our acceleration came out to 1.17. From here, we moved on to trial 2. We used the same exact stationary position for going up, except for here, for going down, the normal force was less than the mass times gravity. So, using our Fnet equals ma equation, we had to subtract our normal force from the mass times gravity. We used our normal force in the stationary position and plugged it into our second equation for going down. And then over here we found the equation m2g minus m1g equals m2a. We plugged in our masses and came out to have an acceleration of negative 0.86 meters per second squared. Okay, so for our second trial, we just used the equations we used for the first trial. m1g minus m2g equals m2a. This is for going up. We used the masses from the data we had over here for trial 2, and we plugged that into this equation. We found that acceleration going up was 0.85 meters per second squared, And then for going down, we used the equation we found from trial 1 again. m2g minus m1g equals m2a. We saw for acceleration and found it to be negative 0.94 meters per second squared.